Hello students, in this video we are going to study the theory of computation, regular language models. We could see some questions from regular language models such as minimum state automata, homomorphism and equivalent grammars. Number of states in minimum state automata. If the length of the string equal to n, then the number of states equal to n plus 2 in case of minimum state automata. For example, if the length of the string equal to 2, then the number of state equal to 4 in minimum state automata, which includes the dead state too. Here, this automata only accepts the string of length 2. So, whenever there is a string of length more than 2, this automata moves to a dead state, and in this dead state, it loops into itself. So, the number of states in minimum state automata for accepting a string of length n equal to n, then the number of states in minimum state automata equal to n plus 2. Consider the next case in minimum state automata, where the length of the string is less than or equal to n. Then the number of states in minimum state automata equal to n plus 2. For example, if the length of the string is less than or equal to 2, then it would accept empty string, string of length 1 and string of length 2. Hence, the number of final accepting state equal to 3. Also, the automata contains one dead state, as the automata moves to a dead state when it reads a string of length more than 2. Hence, the number of states in minimum state automata for a string of length less than or equal to n, then the number of state equal to n plus 2. Consider the next case in minimum state automata, where the length of the string is less than or equal to n. Then the number of states in minimum state automata equal to n plus 2. For example, if the length of the string is less than or equal to 2, then it would accept empty string, string of length 1 and string of length 2. Hence, the number of final accepting state equal to 3. Also, the automata contains one dead state, as the automata moves to a dead state when it reads a string of length more than 2. Hence, the number of states in minimum state automata for a string of length less than or equal to n, then the number of state equal to n plus 2. Regular grammar or type 3 grammar. A production of the form A to alpha or A to alpha b, where a, b are variables and alpha a terminal symbol, is called a type 3 production. A production of the form A to alpha b and A to alpha, where a and b are variables and alpha a terminal symbol. In this production A to alpha b, the variable b is on the right side of the terminal symbol alpha. Hence, it is called a right linear or type 3 regular grammar. Consider the production A to b alpha and A to alpha. Here the production A to b alpha, the variable b appears on the left side of the terminal symbol alpha. Hence, it is called a left linear type 3 or regular grammar. A regular grammar is either a right linear or left linear. A linear grammar need not to be a regular grammar, but a regular grammar is always a linear one. Consider the examples: s to alpha s or beta s or epsilon is a regular grammar, as it includes the productions of the form A to alpha b and A to epsilon. Here A to epsilon is allowed in type 3 grammar. Next example is S to alpha S or beta S or alpha or beta, where alpha and beta are terminal symbols and S is a variable, and it is of the form A to alpha A, comma A to alpha, which is a type 3 production. Hence, we could see the type 3 productions can only form a type 3 grammar. Regular languages are closed under all set operations like union, intersection, complementation, etc. Consider a property of regular languages, homomorphism. Homomorphism is a function from strings to strings that respect concatenation. That is, for any x, y element of sigma star which represents set of all strings, h of x y equal to h of x concatenated with h of y. Any such function is called a homomorphism. In homomorphism, we are finding a homomorphic image of the string in language L. If L is a language on alphabet sigma, then its homomorphic image h of L is given by h of W, where W is an element of language L. Next, we could see homomorphism for regular expression for a language L. Regular expression is an algebraic description of a language. For example, A star is a regular expression for language L equal to set epsilon A, etc. Homomorphism for regular expression R is obtained by applying homomorphism to each symbol in R. For example, consider the function h from the alphabet sigma to tau star, where sigma equal to set alpha beta and tau equal to set a b c. The function h is given by h of alpha equal to ab and h of beta equal to bbc. If regular expression R equal to alpha plus beta star into alpha alpha whole star, then h of L is given by AB plus BBC whole star into AB whole star. Equivalent grammars. A language can be generated by many grammars. Two grammars G1 and G2 are equivalent if they generate the same language, that is, L of G1 equal to L of G2. For example, consider the grammar G1 which has productions S to ASB or lambda. When we generate the strings using this production, we will get the language as a raised to n, b raised to n, where n greater than or equal to 0. Consider another grammar G2 which has productions S to AAB or lambda, A to AAB or lambda. When we generate the strings using these productions, we will get the same language as a raised to n, b raised to n for n greater than or equal to 0. Hence, G1 and G2 are equivalent grammars. Let us check one question from this section. Consider the grammar G1 which has productions S to ASB or BSA or SS or lambda. And consider another grammar G2 which has productions S to ASB or BSA or SS or SSS or lambda. When we generate the strings using these productions, we will get the same language. Hence, these two grammars are equivalent in nature.